The shared responsibility model for commercial cloud infrastructure assumes a benevolent host. This architecture rejects that premise. We treat the host operating system and hypervisor as a hostile memory environment. This is the Januscape vulnerability, a flaw in the Linux KVM hypervisor that sat dormant for 16 years. Tech companies offer $250,000 bounties for exploits exactly like this, which allow attackers to escape a virtual machine and execute code on the underlying host. To test the underlying hardware can be subverted without triggering software alarms, any effective security model must assume the hypervisor itself is an active, privileged adversary. Detecting a compromised hypervisor relies on a strict physical law. Observation requires energy. If a hostile hypervisor pauses a virtual machine to inspect its memory, it must consume shared CPU cycles. This timing diagram plots CPU cycles against execution flow. A continuous workload runs smoothly until a hypervisor interrupts, creating a time dilation gap. The Enclave measures this cycle variance against a 3 standard deviation threshold. Exceeding this limit provides unforgeable proof of tampering, triggering a thermodynamic violation. To defend against rapid memory extraction and automated heap sprays, the system operates in a permanent siege state. This memory block diagram illustrates our strategy. Instead of caching freed memory, we starve the adversary by forcing immediate physical page deallocation. By overriding default allocator behaviors, setting memalloc purge delay to 0, and issuing a madv don't need system call, we physically evict data from RAM. By instantly destroying cached, dirty memory pages, the architecture ensures a hostile hypervisor has absolutely nothing to scan. When a thermodynamic violation is detected, the Enclave initiates a fail dead protocol. This volatile RAM schematic shows the temporal stakes. The system must obliterate ephemeral keys before the hypervisor completes a memory snapshot. To prevent compiler optimization, a write volatile instruction physically scorches the memory with high entropy noise. Finally, a hard process abort flatlines the Enclave instantly. In a hostile environment, data confidentiality supersedes system availability. Failing to a dead state permanently denies the adversary access to the asset. This kinetic response creates an operational paradox. While volatile RAM must be scorched instantly to prevent theft, destroying encrypted data at rest during an active litigation hold violates federal anti-spoliation rules. This schematic illustrates the Sanitization Interceptor governing the data lifecycle. If an automated erasure command targets data under a legal hold, the Interceptor explicitly blocks the request. The action is logged immutably, aborting the erasure. The architecture enforces absolute cryptographic security against physical threats, while maintaining strict legal compliance.